All right. So yesterday when we were talking about this latent heat thing, we said latent heat is really just potential thermal energy, okay, or the change in potential thermal energy. So if I want to melt ice, I have to add a lot of heat in order to get the molecules of water to move further apart and change state from solid to liquid. Okay, similar thing happens when liquid water is turning into a vapor. Okay, the molecules reach a point where they really essentially can't move any faster. Okay, in the state that they're in, so you continue to add energy, large amounts of it, and they will move further apart, which will turn them into a gas and allow them again to have more room to speed up, okay, and move faster in that state. Okay, so what we looked at was a graph that had generally this shape. And what I always tell people is when you've got a heating curve question, and you know you have a heating curve question if you're dealing with more than one state of water. Okay, heating curve will always be about water. At least in Science 10. Okay, I mean there's a heating curve like this for essentially everything. Okay, but we deal with specifically water. In your specific heat capacity questions, did anything ever change state? Right, and there's only ever one step in those. Okay, so a heating curve question, you know you're dealing with water, and you know it's changing state at least one time. Okay, so what we want to do is just roughly draw out that graph. We don't want to draw the axes and everything. I never said that, because you would never draw an improper graph except in this case. Okay, you don't need to put axis on here. You just need to know this is 0. Okay, this line here is at 0. This line here is at 100. Okay, and you just need to mark your starting point and ending point so you can figure out how many steps there are and identify what formulas you have to use. Okay, so I would probably give you a mark for this. This would be like your givens. Okay, for this question. So we start at minus 15 degrees. So that's there, and we're going to finish at steam at 150 degrees. So maybe I need to make that line a little longer. Okay, that's my ending point. Anywhere where a line changes direction is a new step. Okay, so my first step is here, where I have to change the temperature of ice from minus 15 to 0. What formula do I use for that step? MC delta T, because there's a temperature change. All right. And then I have this step. I have ice at 0 degrees, and at the end of this step, I will have water, liquid water, at 0 degrees. So that means I'm going to be using E equals MLF, because I'm changing state from solid to liquid. Okay, so we use the latent heat of fusion, which for water is 333 joules per gram. Okay. At the end of this step, I have liquid water at 0 degrees. If I continue to add heat, I'm going to heat up the water. The water is going to change temperature from 0 to 100 degrees. So for that, I'm going to use E equals. Which one do I use when there's a temperature change? MC delta T, the one that has temperature change in it. Okay, and then up here, I start out with water at 100 degrees Celsius, and at the end of this step, I will have steam at 100 degrees Celsius. So this will be E equals MLV, right? Okay, and at the end of that step, we said we'd have steam at 100. At the end of this step, we have steam at 150. Temperature is changing, so we're back to E equals MC delta T. How many steps are there here? 5 steps. That's the most you're going to have. Okay, probably on a test, I would not give you a 5-step question simply because if you can solve one of these with 3 steps, you can solve one with 5 steps. Okay, that's my thinking anyway. All right, so expect that I'm probably not going to give you one that long on a test because it's not really effective use of time. All right, so as long as you know, I mean, you've got to be able to do a 3-stepper because you're going to get probably 2 temperature changes and 1 state change. Okay, something like that. All right, so now I've identified all my steps. Now I need to do the calculations. So for step 1, I'm using E equals MC delta T. Okay, the mass we said was 250. Okay, and it's ice, so I have to use the specific heat capacity of ice, 2.116 joules per gram degree Celsius. And the temperature is changing by how much? 15 degrees. Remember yesterday I said that's the mistake I see very often is that people would do the entire temperature change for the whole question, which would be 165 degrees. Okay? Ice is not changing by 165 degrees. All right? It's only changing from minus 15 to 0. All right, so we've got that step. Okay, for step 2, we'll do the calculating in a minute. Okay, For step 2, we have E equals MLF. All right, is the mass still 250? Will the mass be 250 through the whole question? Yes, because I can't create matter and I can't destroy it in a physical change. Agreed? Or in a chemical change or any other change for that matter, right? Because that would violate the law of conservation of mass. Okay, 250 times 333 joules per gram. All right, step 3, we're heating up the water. So we said we would be using E equals mc delta T. So that's going to be 250 times now what am I heating up? Water. So I have to use the heat capacity of water now, which is 4.2 joules per gram degree Celsius times 100 degrees Celsius. Okay, step 4, we said is E equals MLV. All right, so we'll have our 250 times 2,260 joules per gram. That's the latent heat of vaporization for water. And then step 5. Boy, my columns got a lot skinnier as I went along, didn't they? Okay. E equals mc delta T. So 250 times the specific heat capacity now of steam, which is 2.02. Okay, and then we're changing that by 50 degrees Celsius. Okay, so is the math of any of those steps very hard? No, you don't even have to manipulate. You just got to plug the numbers in the right way. Okay, so really these are pretty easy marks when it comes right down to it. All right, so we'll do all of our calculating here. So our first one was 250, okay, times 2.116 times 15. All right, so we got 8,100 for our first step. Oh, I missed a 1 in there. Yep. Okay, so now it's 7,935, not 8,100. Okay, so we've got that, and then we got to, we'll add that to, and I'll just put them all in here. We'll just do them all in brackets kind of a thing. Okay, so we've got 250 times 333. Okay, plus our next step, which was 250 times 4.2 times 100. Okay, plus 250 times 2,260 plus 250 times 2.02 times 50. You don't have to do it that way on a test or anything, guys. If you want to do each step separately and add them up, that's fine. Okay, so our final answer there is that takes 786,435 joules. Okay, is that a lot of energy? Yes. How much water is 250 mils? A cup. Yep. Okay, 1 cup of water. Okay, 1 cup is 250 milliliters. All right, so it's not very much water, but that's a lot of energy in order to turn it into steam at 150 degrees. Is that making sense to everybody? All right, I want you to do the questions that are like this on that worksheet from yesterday. Okay, so on the back of that worksheet, there's what, 8 or 10? Okay, there's not very many. Some of them obviously are easier than this. That's the most involved they can get, 5 steps. Most of them are less than that. Okay. Right, and we'll go through any that give you trouble. All right, guys. So we're just going to look at what we're doing tomorrow here. You are not going to be handing in a formal lab report for this lab. Okay, I'll tell you that right off the bat. I told you I wasn't going to assign you anything else for the remainder of the semester. I'm not. Okay. What we're going to do though is do this as an activity. Okay, just to see if we can calculate and see if the value we get for the heat of fusion of water is the same as the value you've been using, which is. Oh, that's the specific heat capacity. What? 333, right? Okay, we're going to see if the number we get is going to be close to that. I'll tell you, in the past, we've been pretty close. Okay, we generally get numbers between 290 and 350. I know that seems like kind of a big range, but you got to remember, are we using absolutely pure water? No, we're gonna go out and gather snow from outside. Okay, I mean, people have probably walked. We'll try and get as pristine a snow as we can possibly get, but I mean, it picks up stuff as it falls, and it's not perfectly pure water. It's got impurities in it that are going to change the heat of fusion of it. Okay. So what we're going to do tomorrow is this: we're going to go outside and fill up like a big beaker full of snow. We're going to pack it. Okay, so that it's got lots and lots of snow, and we're trying to eliminate as much of the airspace as we can. Okay, make it kind of just a big block, okay, of snow. All right, then we're going to add the specified amounts of everything here. It says carefully measure 200 mils of water in a graduated cylinder. Okay, we need to know that we've got exactly 200 mils. Okay, we're going to stir the water, measure and record the initial temperature, and then we're going to add the ice to it. Okay, so we're going to take our, well, not ice, it'll be snow in this case. Okay, we're going to add it and we're going to stir, and we're going to continue stirring. Not with the thermometer. Okay? People make that mistake. Is the thermometer a stirring rod? It is not. If you try to use the thermometer as a stirring rod, you will add impurities to the snow because you'll break the thermometer, and all the ethyl ether that's inside the thermometer will come out, and it stinks really bad. And there's all that sharp stuff, glass, yeah, that comes off. It's dangerous. Okay, so you don't want to stir with the thermometer. Okay, you stir with the stirring rod, but the thermometer has to stay in there because we want to record what happens to the temperature. Obviously, the temperature is going to decrease. Okay, when we put the snow in. How far? What temperature will the water go down to? Yeah, close to 0. It doesn't always go down to exactly 0, but it goes somewhere between 4 and 0 degrees, and then it stops. Okay, and it stays at that temperature, okay, for the rest of the experiment. Once the temperature starts to flatten, then the experiment is over, and we have to quickly take all of the remaining ice out of the mixture. All right, is everyone following me there? So what we're doing is we're using the water we initially added to the beaker. Okay, so we have the beaker here, and it's going to have had that 200 mils of water in it. This water is going to change temperature, and we're going to use the mass of this water, and since there's 200 mils of it, the mass of it is 200 grams. Okay, and we know the specific heat capacity of it. Agreed? And we're going to record its change in temperature, however much that's going to be. Let's say it's 15 degrees. Okay, we'll be able to calculate how much energy it lost to what? Where did the energy from the water go? Into the ice. Okay, so we're going to be able to calculate how much energy the water lost, and thus the ice gained. Everybody follow me here? Okay, that's essentially what we're doing. Just a little bit of algebra here. Now, this is the mass of the water. This is the mass of the ice. How am I going to know how much ice actually melted? Exactly. I'm going to have more water in here now. Remember, I said as soon as the temperature starts to flatten, you're going to reach in and scoop out all of the ice that's in there. Okay, all of the snow. Get as much of it out as you can. Okay, and you're going to have more water in here than you had before. However much more water there is, that's how much ice melted. And it's, let's say that it ended up being, I don't know, because I'm making up numbers here. I'm not going to get the right answer. Okay, but we'll say that there's 25 milliliters of water extra than there was when we started. Well, that means 25 grams of ice must have melted. So we would know this number is 25 grams, and we'd be able to solve for LF. I don't think that comes out to anywhere near the right number because I just made them up in my head, but it worked. It'll work. Okay? Tomorrow you'll get a number around the right number. And we'll do a few trials of it just to make sure and get a good average of things. Probably take snow from different places so we get kind of a smattering of different snow samples as well. Okay? Does that sort of make sense what we're doing there? Okay? It's not really difficult, and okay, it's just going to confirm and allow you to see what I've been telling you will happen. Okay? And that is that when there's a state change going on, there's no change in temperature, right? Okay, so that's kind of what's going to go on with that, and then we'll work on some of the analysis stuff tomorrow in class. Okay, as a class, we'll kind of just go through those questions and have you write them down on a sheet of paper, just so you have some notes related to this. Okay, because there's often questions on the unit and final exam about that lab. Okay, so you guys will still have something there to go on, okay, when the unit time comes, but you won't have to write up the full lab report. Okay, does that sound like a fair deal? All right. So we got about 5 or 6 minutes left here. exam procedures. That's what I was supposed to review with you today. I knew I was forgetting something. Okay. Okay, so guys, a few people have come up here about 5 and 6. Okay, just because they are a little tiny bit tricky here. Right? It's asking for number 5, how much heat is given off when 2 kilograms of water at 0 freezes into ice at 0. Okay, so if we draw like we're supposed to as our first step, okay, a little miniature heating curve of water, and we mark our starting point and ending point. Here's our starting point, water at 0. Here's our ending point, ice at 0. How many steps is that? Just one, right? We don't have any temperature changes. All we're doing is freezing water that was already at 0 into ice that's also at 0. So this is our only step. So our only step is E equals MLF, right? So it's 2,000 grams times 333, which gives us 666,000 joules. Okay, and it's very similar for number 6. It asks how much heat is needed to change 60 grams of water at 100 into steam at 100. Well, if we're looking at our heating curve there, we start with water at 100 and we end with steam at 100. That's only one step. Okay, that's why it's so important to mark beginning and ending points on your heating curve so you can figure out how many steps and what steps you have to do. All right, does that sort of make sense? Okay. Any other ones giving us trouble? All right, so for number 7, we want to find the total heat required to melt 1 kilogram of ice at minus 20. Okay, so it says here the final temperature is going to be 0 degrees. So all we're doing is melting it. We're not heating the water after that. Okay, so if I'm looking at my heating curve here, all right, I'm starting at minus 20, which is down here, and I'm ending here at 0 degrees Celsius. How many steps is that? 2. I got to heat the ice to 0, then I got to melt the ice. All right, so my first step is to go E equals MC delta T, and that's going to be 100 grams, because it's 0.1 kilograms, times 2.116 times 20 degrees. Okay, and then my second step will be to melt that ice. Right, so that'll be E equals MLF. So we'll have 0.1 kilograms times 333. Right, so we're looking at 33.3 joules for this step, and $4.232 for the heating of the ice. All right, so when we add those together, sorry, what am I saying? Not 0.1, it should be 100 here. Sorry guys. So my numbers here should all be bigger. And this should be 4, 2, 3, 4, 2, 3, 2, yeah, 0. Actually, that should be, no, 33,000, that was right. That 0 shouldn't be there. Okay, then we're right. Alrighty. Sorry guys, I messed that up with the grams there. Okay, everybody with me on that one? So it's 2 steps, okay? And you got to convert the kilograms to grams better than I did. I remembered to do it here and then forgot and then entered it as 0.1 all the way along. Okay, other ones. All right, keep it going then. 211.